For those of you who don't know me, my name's Tom, and today I'm going to be talking about my final year project, which was looking at reducing landing earthworks through the use of computer-aided design. We'll have to click. So forest landings make up an integral part of modern whole tree harvesting operations. If a landing isn't properly located, designed, or managed adequately, serious consequences for the environment, safety and productivity can occur. However, despite this, little work has been done looking into how to better optimize these key pieces of infrastructure. Conventionally, a detailed design of forest infrastructure is carried out using manual surveying methods, which can be time-consuming and challenging. Computer-aided design programs such as Road-Eng provide an alternative pathway which is both fast and flexible. Presently, forest companies using Road-Eng are primarily concerned with road design, with landing design being considered a niche application. So the main objective of this study was to use Road-Eng to redesign existing landings with an equivalent surface area using less earth material. To achieve this, the project was carried out as a desktop study, with the two key pieces of data being digital elevation models and aerial imagery of 15 landings across 3 different regions, which were the Hawke's Bay, Tasman and Gisborne. This data was sourced from Land Information New Zealand's free to access spatial database. So fundamentally, the method was based on taking a digital elevation model of an existing landing, which you can see here, and then transforming it into a digital surface model of the original terrain using tools in Road-Eng. This original surface layer was then used to redesign a new landing and compared to the original using the average cut depth, which was calculated by dividing the amount of cut volume it took to construct each of the landings by their respective surface areas. Now, you might be wondering why I didn't just directly compare the cut volume that was used to construct the landings. And this was due to the fact that Road-Eng only allowed me to design the new landings to within 100 square meters of the original landing area. So that was about a difference of 10%. So, and obviously, because the surface area is a function of the cut volume, comparing 2 different landings that had took 2 different cut volumes to construct, but also had 2 different surface areas wouldn't have made for a fair comparison. So as you can see, there was quite a lot of variation within and between the different landings. And some of these values were obviously infeasible. So anything greater than 8 meters average cut depth, as well as any landings that redesign landings that increased the average cut depth from the original design, were treated as outliers. After excluding these outliers, it was found that on average, the redesigned landings had an average cut depth which was 34% less than that of the original designs. To better understand this data, I also calculated the percentage difference between each of these and presented it in this graph here. Out of the feasible designs, the greatest improvement was 78%, whilst the lowest was 6%. The 2 negative outliers that you can see on the right here were 21% and 26% respectively. And like the other infeasible data points, I suspect were a result of errors in the reconstructed digital surface model. So in analysing the data to determine some of the driving factors behind these key differences, it was found that it really came down to how well the original landing's edge followed the contour of the terrain. Now, intuitively, this makes sense because the greater the difference in elevation between the landing surface and the underlying terrain, the more earth material you need to build this landing up to that desired elevation. So when that landing edge follows the terrain more closely, you need a lot less earthworks to achieve an equivalent landing area. Now, although these results were promising there were a number of limitations to the approach that need to be discussed. The first of which was that it wasn't possible to infer the construction method that the contractor had used from the digital elevation model. This meant that I could have been comparing landings that I'd designed using cut and fill to landings that have been constructed using end haul. Also, design decisions around the location and 2D geometry, the landings that have been made by the contractor and harvest planner were unknown, which could have been key to the overall success of the operation. And finally, the reconstruction method was limited to really simple scenarios with relatively uniform terrain and couldn't reconstruct complicated topographical features, which meant I had to be quite selective about the landings that I chose to reconstruct. This highlights the need for a future study that would further reinforce the findings from this report. This study would want to capture the digital elevation models before and after construction, which would negate the need to reconstruct one layer using another. This could be achieved through UAV-based remote sensing and would want to work closely with the harvest planner and contractor to understand some of those driving decisions around the shape and location of the landing. So to summarize, digital elevation models of 15 landings across 3 different regions were redesigned, were taken from Land Information New Zealand, and new landings were redesigned in Road-Eng. It was found that these redesigned landings had a reduction in average cut depth of 34%. Showing that it was in fact possible to create a landing with an equivalent surface area for a small amount of earthworks. And although these results were promising, there were a number of limitations to the methodology, but a future study could potentially reinforce the findings from this. That brings me to the end of my presentation. Is there any questions?